Okay, let's try that. The area bounded by y equals x, y equals 1, x equals 0, revolved around the x-axis. This is one of the most basic problems I can give you. And there's, we're used to be able to kind of push at a quicker pace. I get that this is difficult stuff. So just take a minute and see if you can draw the appropriate shape and revolution and see if you can come up with the slice. If you can do those pieces, then we can go ahead and start our integration. So just take a minute, see if you can do it. Okay, so wherever you're at, I'm going to draw exactly what you're supposed to have. Y equals x looks like this. Y equals 1 looks like this. And x equals 0 looks like this. So you have this triangle. We got the triangle. So when you flip it around the x-axis, you get that shape. Now, you can see it makes a point at the end, right? Okay, if I held this container in my hand, would it hold water or would water fall through? It would hold water because of that point at the end, right? It's not completely hollow all the way through. But if you were to slice it, let's say I slice it in the middle, you can see that this piece would rotate to here, okay? And the top piece would rotate to there. So this is a washer. It's actually talking about these problems with some other teachers the other day, and there's definitely a disparity in students in terms of cognitive development and understanding spatial reasoning. Spatial reasoning is not something we spend a lot of time on in mathematics, is it? We talked about in geometry that you guys would do 4 times as many cross sections. So you would take a cylinder, you cut it one way, and you get this cylinder right here. If I slice off the bottom of the cylinder, what shape do I get? Circle. If I slice off the side, what do I get? A rectangle. You see, if you slice the side, you're getting a rectangle. What if I slice it at a diagonal? What are you going to get? You're going to get an oval. So, it's those type of spatial reasoning pieces that I know that they're challenging, and it's kind of like you can ask, well, why do you get that? It's like, well, I don't know. Make a block of cheese in that shape and start cutting it and see what you get. It's hard to reason through that. So I get this washer shape, and here's what I do. I take my washer, which I think I've done a really good job of drawing. And what I do is I like to label the center of it, and I then like to label that portion and then the top portion. So what makes the middle? Y equals 0. What makes y equals x? What makes the top? Y equals 1. So those are my 3 parts, right? What is my width? Is it dx or dy? Dx. So this is a horizontal integration. So I set up my integral. I have my pi times, what's my large R? Watch this, everybody. What is the distance from 0 to 1? 1. You took 1 minus 0, and you got 1. Square it is 1. Minus, what is the little radius? What's the distance from x to 0? X. Square it. X squared. Dx. My integration. What are my bounds? I start at 0. Is everybody convinced you go to 1? Okay. So, we don't need to finish it off, do we? You know how to set it up. Okay? Let's set up one more, and then I can give you the worksheet. Okay? And you can practice. Yeah, it's so rarely do I start for you guys with the most basic of problems, because usually, you know, we catch on to it a little bit more quickly, right? You're more advanced learners. So I've started doing, I pulled the notes that I had done last year. When I had done the area problems and the disk problems, I started by doing easier problems. Yesterday, I pulled what I did last year and the year before, and you know, we had the same type of challenge. I need to start with more basic problems right away. And instead of trying to teach a lesson, say, okay, now I can do washers in one day, it really needs to be spread over more days. And that's fine. We have the time to do it. We're in section 6.2 right now, and it's, you know, just barely done with third quarter, so we're good to go. But yes, please do. So, well, okay, good question. Think about it. A washer, is it two-dimensional or is it three-dimensional? It is three-dimensional, okay? So I have the two-dimensional top that we found the area of, which is pi times r squared minus r squared. But a washer is three-dimensional. It does have volume. So the way you calculate the volume is you multiply it by dx, which is your width, and then we add up an infinite number of those by putting it through the definite integral. That's what's happening. Okay. All right, let's try this one then, okay? Let's do the area bounded by y equals the root of x. X equals 1. X equals 4. And y equals 1. Rotated around y equals -1. See if you can get the drawing, okay? Get the drawing, see if you can, you know, come up with a washer when you slice it. Just start with that, okay? Okay, I'm going to start drawing the shape. Well, difficult shape to draw. The idea is, first of all, did you come up with this kind of triangle type shape up here? When we spin it around, the line y equals -1, how large is the diameter of the hole in the center? The diameter. 4, right? So it's 2 units from -1 to +1. So that's your radius of that inside hole, okay? So as I take so here's really the idea, okay? You don't even have to really be able to draw the whole picture. What you have to be able to come up with is that area on the top, and then understand that when you rotate it around y equals -1, you are going to come up with an empty space in the middle, right? It doesn't have to be an empty space all the way through. The last one didn't have an empty space all the way through, okay? It wasn't hollow. This one is hollow, isn't it? But when you slice it in the middle, you come up with, as we said, this washer. Yeah. So it's going to switch. So I draw my washer. Does it have thickness of dx or dy? Dx is horizontal thickness. I draw my line down the middle, which is y equals -1. What creates the y equals 1, and what creates the top? So when people wonder about the integration process, again, we just have our integral, all right, pi times, I have to now calculate my little radius. My little radius is equal to the distance from the top to the bottom. The way I find distance is I take the top and I subtract the bottom. So little r is equal to 2. Squared is 4. The distance of the larger radius is equal again to the top minus the bottom. So square root of x minus -1 is, and you got to square that. So square root of x plus 1, quantity squared. Right, x plus 2 roots of x plus 1, and then you take the antiderivative, you minus 4 off that. And go ahead. Bounds. The bounds, when you look at the area, okay, if you were to integrate the area, where would you start? 1 to 4, right? That's the same. Okay, whatever you would use to calculate the area is going to be the same as what you would do for the volume, okay? So we're going to go from 1 to 4. A little bit harder? Okay. Well, from our drawing, we saw that we x equals 1, x equals 4 were those boundaries. So they do happen to intersect at this spot and this spot, which have x values of 1 and 4. Okay. All right, let me pause this and I'll